In today's video, we are going through exercise 2.12 from the Art of Electronics. And in this exercise, we need to basically look at a distortion for an amplifier. So the question says we need to calculate the predicted distortion for two amplifiers that are described in the paragraphs above at the two output levels that were measured. So the two output levels were 0.1 volts and 1 volt. The two amplifiers that the question is talking about is one with a grounded emitter and a second one with a resistor added between the emitter and ground. So first of all, let me quickly explain what the distortion is talking about. So the voltage gain of a NPN amplifier changes with the current through the collector, and as the collector changes, the output signal also changes. And we have two equations from the book that describe the change in gain compared to the change in output voltage. So the equation that you see now is the grounded emitter amplifier, and the equation on the bottom is basically for a emitter amplifier with a resistor added. As you can see, the change in gain is reduced by this equation over here, which is RE divided by RE plus RE, capital E. So this RE is internal to the emitter, and this RE is a component that you add to the circuit externally. So as long as RE is much bigger than the intrinsic RE, we will get a gain reduction by adding a resistor to the emitter of the NPN amplifier. If you want to learn more about the NPN amplifier, I have done a few videos on this previously. So first of all, I'm going to talk about the grounded emitter amplifier and basically solve the two cases that are asked by the question. So it's 0.1 volts and 1 volt. So grounded emitter amplifier with a 0.1 volt output. We basically have this equation from the book. So what we're going to do is drop in 0.1, which is our output variation or output delta, and our V drop is 5 volts, and that's also described in the question. So that's basically biasing for 5 volts and setting a 1 milliamp current that's described. Now this gives us a distortion or a gain distortion of 0.02. However, this 0.02 contains the linear and the non-linear components. The non-linear components are approximately 1/3 of the maximum delta that we have calculated over here. So multiplying this by 0.33 gives us our distortion for a 0.1 volt output variation. So the non-linearity or the distortion for this circuit and this output level would be 0.67%. Now increasing the output level to 1 volt swings, we basically have the same equation. However, we will replace the 0.1 in terms of the delta V out with 1, which gives us our maximum as 0.2 over here. And taking a 1/3 of that gives us approximately 6.7% of distortion for this circuit. So that's the solution for the grounded emitter amplifier and the calculations. Now if you compare them to the calculations that are given in the book, they are very close to what was measured by the author. Now for the second part of the question, we need to look at a emitter amplifier where we have added a emitter resistor to the circuit. Now the question tells us that we have a 250 millivolts of drop across the resistor. We can use this information to calculate what the emitter resistor value is going to be. So that gives us roughly 250 milliohms because the emitter amplifier has been biased with a quiescent current of 1 milliamp. However, we don't need the resistor value if we are going to use this equation over here, because IE/RE is basically the voltage of RE, and we have been given that in the question or the paragraphs above the question. So again, we have this equation from the book. So that's what we're going to use to do the calculations. So our voltage variation or delta V out is 0.1 in this case, divided by 5, which is the biasing point for the circuit. And we multiply that by 25 millivolts over 275 millivolts roughly. And that gives us a distortion of 0.061. So you can see when you compare this distortion with a amplifier without the emitter resistor and one that is fully grounded, the distortion is reduced by 10-fold approximately. So when we have a 1 volt output swing, a lot of this will stay the same. Basically, we're going to use the same equation over here and just replace the delta V out with 1. So in this case, we get a distortion of 0.613%, which is still 10% or approximately a tenth of the distortion we had with for the circuit without a emitter resistor. Now the only thing that I basically need to explain in this equation, because this is just completely from the book, is the VT. Now if you wanted to learn a bit more about this, you can check out the transconductance section in the book, which is on section 4. So you can look at equations 2.8 to 2.10, where it tells you this equation over here where K is the Boltzmann constant, T is the temperature in Kelvin, and Q is the electron charge. Now calculating all of that out basically gives us 25.3 millivolts, which is what we're putting into this equation over here. So all the question is trying to show is that adding an emitter resistor basically helps with reducing the non-linearity and reducing the distortion. Now, if you're following along in the book, there are some graphs that show you the type of distortion that this will cause. So check that out. Basically, as the voltage goes up, your gain starts to reduce. So you start to get rounding off. Basically, if you have like a triangle wave starts to turn more rounded as you start getting closer to VCC as the gain is reducing. So thank you for watching today. That's all I have to share with you for this question. If you have any questions, please let me know in the comment section below. Don't forget to like, comment, and subscribe. Bye for now.